welcome everybody to August Lunch and Learn, but we're doing a happy hour this evening. This is featuring Future Grid, and Chris will be giving a presentation here shortly. This webcast is being recorded. By participating in this call, you consent that your name, voice, and contributions will be included in the recorded materials. Phones and computers have been muted on entry. To unmute yourself, click the microphone at the bottom of your screen, or if you have dialed in, press *6. For best connectivity, we do suggest joining the webcast first and having it call you. If you need help with that or you're having bad connection issues, please just reach out to me. We would like to have a very interactive webcast today. So feel free to ask questions, introduce yourself over here in the chat on the bottom right-hand side of your screen. You can ask questions there as well or provide comments. And I am now just going to turn this over to Chris, and Charlotte should be joining us shortly. Chris, you have the floor.
Thank you, Angie, and welcome everyone to what hopefully will be an exciting presentation from one of the team down under from the EPRI program. We're proud to be representing our country with our good partners EPRI. What I've tried to do in this presentation is that I'm really against trying to talk about my product too much and go on a bit of a sales spree, because that usually bores everyone pretty quickly. So what I've done when Angie asked me if I wanted to do one of these sessions and share some information, I've really thought about some of the lessons learned from the program with EPRI and other customers we work with, and tried to really share one of the key lessons that we've learned that may help some of you on your journey towards using data and AMI and analytics. So let's give me some feedback. Hopefully at the end, if it did actually help, that'd be handy to know. Otherwise, I'll get going. So who are we? We're based in Australia, but increasingly we've been doing projects in the North American region, and part of the reason for that growth has been due to EPRI and the program we did with them. There's a bunch of logos here. Most of them may or may not be familiar to you because they're from this side of the world. But I think the main message about why maybe we know something and maybe we can help or at least inform you on your journey is because in Australia, most of the distribution utilities, and that's who we work with, the distribution utilities, use our product for solving some of the challenges that we're going to talk about today. And we've had a few new customers that have come on board in the region. Vermont VEC is one through EPRI, and Fortis VEC is the other one we did the pilot with, and I'll talk a little bit about that. And my name is Chris. I'm I guess we call me the co-founder and CEO, but I kind of don't like those terms. I just like to think of myself as the good bloke that helps run this company, Future Grid, and enables the team to do all the good things that I'm going to show you and talk about today, because it's really them who make this happen. So just a quick summary. We participated last year. I think, yeah, it was last year. Was it last year? I think it was. During COVID, with our friends EPRI in the Incubatenergy program. So that was really a really exciting activity for us, and the two partner utilities we worked with was Vermont or VEC and our good friends Fortis BC. And I guess part of the program for us, I mean, being well established in a country like Australia, part of our goal was to work with some engineers and supportive utilities, which this program enabled us to do, to help to understand and translate our product into the North American region. Hence why having a customer in one in the US, being Vermont, another one in Canada, was very helpful for us. And we were lucky enough to have some great teams in both these companies who really helped and informed us, gave us some pretty direct feedback, which allowed us to kind of accelerate our journey to adapting our product to your region and to make sure the things that we've been helping utilities with on this side of the world would translate effectively to yours, and that's kind of our goal moving forward. Just a quick bit of summary of what we tried to do in that project, and then I'll go into some of the things that I learned from it. But it was really around what we call secondary network visibility, or if you're in a different part of the world, you might call it low voltage visibility. But really, the part of the distribution network that is being impacted by the increasing adoption of DER, whether it's electric vehicles or rooftop solar, or in the future batteries. And I think from the project perspective, we delivered it as a kind of a managed service. So we hosted it. We integrated some data from the companies. I think the AMI data from their entire network for at least 1 year, maybe a couple of years in some cases. Took some GIS data or topology information, and we combined all of that to try and deliver some outcomes. And predominantly, it was about visibility using the AMI data of that part of the network to just demonstrate the benefits that could provide to their business, with a particular focus on EV detection in North America, because that's a popular use case or analytical use case that was decided, and that's what we set out to do. And there's a report we could share. I think it's safe to say that when it came to the secondary network visibility component, I think that was good. I think it was a new view that the partner utilities maybe hadn't had before. That was good, but I'll be honest in saying I think the EV detection component wasn't as successful as we liked, or although it did work. I think a bit better for VEC than Fortis. Part of the challenges we learned from that, which actually really helped us to iterate the way we were doing it, or the way it would need to be done in North America to make it, I think, a bit more useful. And we'll be providing some updates to both of those utilities in coming months based on that feedback. But we did detect some EVs, maybe not as many as we would have liked, but I think the whole process for us was really about how to adapt our solution to the network models and topology that those utilities had, and that was a real success for us, at least. And I think we hopefully taught them some things along the way. So that's kind of what we did with EPRI. And now what I'm going to do is maybe give you a bit of context of where we come from, just to give you some idea, to give you an idea of what's happening over here, and then sort of move into, I guess, one of the most common questions that we get asked when I meet a potential customer utility, or even just a stakeholder that we're engaging with in the industry, which we do often, like yourselves. There's a lot of talk about data analytics. I think if you joined early, we were talking about artificial intelligence, and I've got views on that. Maybe I won't go too much into that, but really the most common question we often get asked is, like, I've got all this data, I've done some analytical stuff often, I've got some teams of people doing things, but not necessarily getting the business value yet that they would have hoped, and maybe what they promised. We promised as part of your business case to get that going. And so what I'm going to share with you is some of the examples and maybe a bit of some quick wins that we've learned along the way that you might be able to adopt in your own programs moving forward to help with that. And that's what I'm going to get started with. But first, I'll tell you a little bit about Australia and what's happening here in the DER market, because that's probably interesting. And then I'll get into a few examples at the end about how we're helping solve some of those challenges. There's some takeaways to think about as part of your program. So, there's a lot of talk. I was at Distributech in Dallas a couple of months ago now, and if anyone was there or it's been floating around the conference scene, you'll know the word DERMS, because that's pretty much all I hear. The DERMS, everyone's got a DERMS. You need to buy DERMS. I'm sure you're all talking about buying DERMS. The only question I would ask anybody who's thinking about it is, what does DERMS mean for you, and what is a DERMS? And if you ask 5 people, I think you'll get 4.5 different answers. And that's okay, because it's a new thing. But what I thought I would share is DERMS, to us at least, my definition at least, is I call it low voltage SCADA, or I call it a control system for your distributed energy, whether it's rooftop solar or EVs, and the inverters that really drive that. a bit like you have SCADA to control your, your key assets today, right? But what DERMS doesn't necessarily do is provide, visibility and grid management capabilities to inform those control decisions. That's our view. And we'll share some examples of where we've been working with customers and doing that down the track. But there's a lot of talk about high penetration DER, or what's a lot of DER look like, how that's going to affect my network, etc. So here's a picture that I actually took. I don't think there's the date there. Yeah, 16th of August. So this was, I don't know, is that today? It's a couple of days ago. I just remember I'm kind of one day ahead here. But this is a site that you can go to. It's a public site that gives you the demand mix in the entire, what we call the national electricity market. I guess you could, for those not familiar with our market, it's probably similar to the ERCOT market. Well, it is similar to the ERCOT market because this was like version 1 and ERCOT was kind of version 2 of this design. But as you can see, and this is a particular state I focused on called South Australia, and anyone may be familiar with South Australia because that's where Tesla and Elon Musk deployed their big battery originally a few years back. But also they're famous for wine. So if you ever want a Shiraz, South Australian wine's pretty good. As a bit of a prop for the winemakers down here. And there's plenty of it available because China's not buying it from us at the moment. So might be cheap for our North American friends. But as you can see here, the key thing I wanted to highlight is that yellow is solar. It might be hard to see on the presentation, but rooftop solar is actually, a very predominant generating source, during the middle of the day, and that's what this is showing. So you always see duck curves and things, but this is like a real live example of what happens when you get a lot of rooftop solar and some utility scale solar, and the mix, that contribution mix during the day at least, that is making to that network. And that network's probably, I don't know, 1.5 million homes, so modest and probably some sizes, but that gives you an idea of that. And just for example, they've got something like 50% penetration of rooftop solar across that network right now. And the average in Australia is something, I don't know the exact numbers because it changes and depends on who you talk to, but essentially it's something between 35% and 40-something% is the average penetration rate of rooftop solar in Australia now. So every distribution utility to a large degree is being challenged by, this new evolution. And I'll show some examples of what that really means. So yeah, that's just really interesting, I think, for those who are talking about it. So this is what it really looks like. And as you can see, in this particular state, you've got a lot of wind as well, which, to be honest, I didn't even know until I took this photo for this presentation. But when you talk about net zero, which is the flavour of the month at the moment for everybody and governments, you can see this state's kind of feeling pretty comfortable. They're on that path. You can see a lot of wind here. There's been a lot of storms actually over the last few days. You can see that wind has really kicked in. A lot of storms and therefore not much sun. Interesting. But as you can see in the evening, which is the common problem, the evening is all gas or other, we would now say fossil fuel based technologies, gas predominantly here, or coal often in other parts of Australia, to, take the load in the evening load as everybody, I guess they come home from work. Maybe they don't come home from work anymore. But anyway, when the sun goes down, you can see that. So it's pretty clear what's going on. But that's what it looks like, in a world where you've got kind of 50% penetration of rooftop solar, which I think is kind of an interesting view of the new world that we're all moving to in various paces. So now, from a network perspective, a distributor, so what? We talk about it all the time. And for those who are not familiar or interested, this is what it looks like. And I've just taken these screenshots, I think last night, for this presentation, just to show you real life examples from customers of what it means. And this is really it. So don't worry about the voltage levels. And these are Australian levels because I took it from an Australian site. But it's basically the same for you. You've just got a tighter profile for your voltage levels that you operate with. But the idea that I'm really just trying to show is there's a voltage rise occurring, and you might be able to see it during the day, right? Voltage rise, and it's going outside of the limits that they're regulated to maintain, like most of the time. and then, obviously dropping and maintaining a normal level. And the interesting thing, and this is kind of the giveaway often, is that load is increasing. This is current down here. So load is increasing during that day, but voltage is rising. Most people would, it's kind of the opposite of what we would normally expect. More load usually means voltage drop. But with solar, this is the behavior you start to see, and you start to see it everywhere. And the more solar you get, the more of this voltage rise you get. And that is probably the fundamental issue. And there's load issues and all this stuff, capacity issues as well. But the one thing that everybody is trying to deal with over here, and we're helping with, of course, is voltage rise, and how do we deal with that, and how do we maintain, within regulatory limits, this phenomenon, which, to be honest, I don't think anyone's really dealt with before at this scale. So it's pretty new. So that's what it looks like, right? So you go, wow, okay. The other thing that happens a lot, which I just took another one which stuck out to me, is not only do you have voltage rise, but you have voltage spread, which is something we're starting to see with our customers. Well, we actually see it all the time, and you're going to start to see it more and more. And I think things like EVs are also going to have this kind of phenomenon, I think. So you're seeing go from one limit to the bottom limit, within the course of a few hours. Now, this is probably at a meter level. I've taken this picture, but if you aggregate that up to transformers, your feeders, or your network generally to the substation, then you start to see this view where you're getting these massive voltage swings during the day with these. This is a solar-based, I think, view. But if you've got a lot of EVs in the future, which I think is going to happen really quickly, particularly in North America, you might have a slightly opposite trend, but it will be a very similar pattern where you're going to get a lot of load pull down your voltage, and it might start to stabilize during the day. So the challenge for the distributors now is this line used to be pretty sort of in the middle or thereabouts, and it was pretty stable, give or take. Someone turns on an aircon or something and that impacts it a bit, but it wasn't like this, and it's never been like this. So now they've got to maintain voltage between those upper and lower bounds, and for you, particularly in North America, it's even harder, because your limits and the spread that you've got to play with are in a 240 volt system. We've got quite a big band, but you've got a much narrower band. So the kind of a sensitivity, I guess, in your network is going to be a bit higher. So this is the new problem. It's like, how do I deal with this? How do I manage a network that I've been doing for 100 years and manage this kind of spread? And these are in my opinion, the sort of the fundamentals of what everyone's trying to work through right now. And okay, hopefully I haven't put everyone to sleep yet, but and this is just another point of view that I wanted to add. And there's a lot of, often when you talk to vendors, or I've seen a lot of presentations, and we talk about transformer utilization. Very popular, very common, it's been around for ages. You can do it, you're probably doing it, and that's fine. But what we like to talk about, we do utilization, and we do, but I don't talk about it much anymore in this world, because the utilization itself, and I should have put the utilization curve that matched this actually, now in hindsight, but anyway, I'll explain it, isn't as interesting as maybe it used to be, because of the demand and generation fluctuations. We like to talk in a concept of hosting capacity. And again, hosting capacity is a bit like DERMS, depending on who you talk to, it means different things, and you can calculate it different ways. But for the purpose of this talk, at least, we've got a simplistic version I'm showing now that really is trying to give you an idea as a utility at the transformer level, how much headroom I've got in terms of demand. And interestingly, now you've got to worry about your headroom in terms of generation. There's two things you have to manage. And the interesting thing, I don't know if I want to use this feature because we played with it. Here we go. Interesting thing is here, if you kind of look at the average utilization, just assuming it's a 10 kilowatt transformer, it's single phase, pretty common, I think. If you look at the utilization across these periods, which is, I don't know, a big chunk of the day, utilization will be actually pretty good, because what it's saying is I've got a headroom of about 6 kilowatts for most of the time. It's only down here that I haven't got much headroom remaining. It's kind of where the load's coming in or whatever's happening on this particular transformer. So what we're finding increasingly is utilization in itself is interesting because you don't want them overloaded. The transformers are designed to run over rating for a period of time. Obviously, will degrade their lifespan, but it can happen. But what we're finding is you kind of got to get the balance right between, well, yeah, is it, if I just look at utilization by itself, that may not tell you the whole picture. I've kind of got to look at, well, how much more capacity, whether it's in demand or generation, because I might have some solar, can this transformer handle, and when is it happening? And obviously, you think it's going to happen here, but that doesn't disappear. I might have to erase it now. And when is it happening? And that's really kind of new information, I guess, for planners, people looking at augmenting the network to support, reliability, gives them kind of a new view. So increasingly our customers are looking at these kinds of views or similar, to start to understand with start to feed into their planning and thought processes about, well, okay, when is that happening? What have I got to do? And obviously you start thinking about, how do I manage that in a DER-enabled world with whether it's demand response or other various things. I'll talk a bit about that later. But I'm just highlighting that these are the kind of new things that are coming, or are starting to be used beyond the traditional approaches, and they're kind of interesting. And that's the stuff we're working on with customers in who have got, particularly a challenge with a lot of solar. And it's not just Australia, Asia, for example. That's kind of our neighbors, I guess. Over here, they're also adopting a lot of rooftop solar, probably faster than even we are now. So this is like a thing that's happening to, I think, everybody, and at various paces. So anyway, my point being, a couple of different things. I don't know how to get rid of that. Here we go. You got to manage the voltage now in a new way, and it's much more dynamic than it ever was. Not only do you have to manage the voltage rise or drop depending on which way it's going, you've got to now manage both within the same day. So, like, how do I do that? And now you're thinking about, when you're thinking about your transformers and your capacity, you're thinking not only about demand, which is like the whole demand response, which we've been talking about for a long time. It's demand, but also generation. I have to think about both, and both acting together. So how do I, what's the view, and how do I manage my assets? These are kind of the new things that are coming in these environments. Now, just a bit about our product. I don't know. I said I wasn't going to talk about it, but I am. So I lied. Sorry. But I just wanted to give you an idea of, when we talk about these things, what our product does, and then it'll kind of lead into the next slides, hopefully. And the quick summary is, we take data from, say, your AMI systems, your Itron or your Landis & Gyr or whatever you've got, one of those two typically. Your GIS data, usually your ESRIs or your hexagons, Gs, etc. That's the main ones, and a few others, maybe SCADA, ADMS, but essentially take data from AMI, marry it with your GIS data. We do this, I wouldn't say real time, because often AMI is not real time, although increasingly for our customers it has become more real time. But nevertheless, it's about taking it, aggregating it against that network topology model as fast as it arrives, and that's kind of, so you can get this visibility of the secondary network. And that's really the idea. Once you've got that visibility, you can better understand what's going on. And once you better understand what's going on, you can start to run your analytics over that. But the key thing that we do is it's kind of live and operational, so it's running all the time as fast as the data is arriving. And it is, it's changing. I think probably just one comment, which is interesting, is as your network changes, which is kind of the flaw in most network analytics programs, often they use a model from GIS that was, last year, an export you did, and they do some analytics against it. Your network is changing all the time, whether you're upgrading things or you're switching things, you've got some open points, etc. So what we do is we take in those changes live with the data, and when you aggregate and do your analytics, it's reflective of the network topology at that time. And it's kind of a unique thing that we do. So it's kind of live and as up to date as it's possibly going to be, notwithstanding any errors in your GIS model. We'll get to that later. But yeah, that's kind of the idea. So I just wanted to keep that. And then you output that. The idea is actually not to have another dashboard for your users or your operators. In fact, that, to be honest, we think that's a necessary step to start, but actually the future is really about how does this enrich your existing operational process. So how do we feed this into ADMS? How does it inform your DERMS of the future? How does it help the control center today with faults and other things that can, help them add value today? So the idea is this kind of takes AMI, converts it into something good, or AMI, sorry, converts it into something good, i.e. analytics, and outputs it into your existing business processes so that it's enriching your day-to-day operations, like or planning today is really our goal. And you've got this dashboard, of course, to look at from an administrative perspective. So it's bottom up, I think, is probably the key note, as opposed to SCADA, which is kind of top down. Just keep that in mind for that. But I won't spend too much time on that. Just want to give you that idea. So that's how we do all of those things. Right, where am I? So that's kind of my intro of some of the challenges, some of the problems. And this is where I get all philosophical and say, okay, and this is very common. In fact, I had this conversation exactly yesterday, and it's probably why I put this picture of Mount Everest on here. And if you've ever done a meeting with us, and if you've probably seen this before or a version of it, but we really love to talk about Mount Everest. And the reason we do is because often when we start a conversation with the utility, or we look at an RFI or an RFP or some kind of process, often what's described is the summit of Mount Everest is the way we look at it. It's like there's a lot of analytical functions. They're very fancy, all really good stuff, absolutely, worthwhile pursuits, but they're pretty advanced. And when we start talking to a customer about where they're at, and this is not to be negative to any customers, because I think the industry is in a similar state, and a lot of these things that are happening are brand new and often never been solved before. We're often sitting here kind of, we say, well, we want to get you to base camp. So where these tents are is base camp in Mount Everest, and that you're going to go climb this summit. And what we like to say is, okay, let's get you to base camp first to move you on the way to climbing Mount Everest, but let's not start with an idea that you're going to be at this pinnacle, right at the top here, day one, because it's just unrealistic. And I'll see customers talk about really advanced analytical functions that haven't even really started their base camp. So the idea is get your foundation right, start with some of the basics, do some really practical things that can improve your business value, deliver on some business case outcomes, build the confidence in the business, and then you're on your journey to this peak. But and the common one I hear about all the time is like phase identification. I think I get a conversation about that every day from a utility, and they want to do phase ID, but they haven't even started with some of the fundamentals of their business. And I always say, that's great, it's a noble cause, but I think there's probably some things we could do that would add more value to your business that are simpler with the same data, like right now. So let's let's talk about that. So there's kind of the aspirational goal, which is absolutely something that we always want to help our customers move to, but we got to start, here, and let's get you to base camp so you're ready to rock and roll, as you build your capabilities and strength and fitness towards, to that sort of analytical outcome. And that's kind of my experience anyway. Love it or hate it, on the success of these kinds of programs, whether you're using our product or anyone else's, it doesn't matter. I think it follows the same pattern that even if you're building it internally too, you're still going to get these basics right and figure out what are the key things that the business can add value to right now, rather than, some really advanced stuff that will be good, but it's, it takes a lot of time, a lot of effort, and often I've seen them fail for those reasons. So I won't go into too much detail. I think these slides will be available, but this is kind of, it's a lot of words. To a degree, I find it a bit too much words, but there's really just a couple of steps. And we've found this works a lot of the time. And, I'm fortunate to have worked with many utilities around the world, mainly on this side of the planet, but it kind of seems to apply equally to everyone. And, the first one is obviously your integration. I won't touch on that. I mean, that's kind of to many an obvious one. You've got your data in various places today, so bringing that together is important. I don't think we're unique in that case, but that's sort of something you solve. But once you've kind of got your data into data together, and companies like FutureGrid and probably others have abilities to help you there, putting it into one place or putting it into an accessible location is kind of your first step, so that you can do what we call visualization, which are those graphs, the maps, etc. Now, we have a product that gives you all that visualization out of the box, but equally you might find that just visualizing it into your GIS, might be also, something you want to do. It doesn't really matter. The key point is you get the data together, which is a project in itself, and start to visualize it, and visualize it in the context of some of those graphs I showed you, which are just graphs, I know, but important because they give you some context to start understanding what is going on. And the most important thing, which is kind of is really understanding power quality over intervals. And it's a long conversation about that. Obviously, everyone's got their interval data, their kilowatt hours or kilowatts on your meters, for those who have smart meters. But increasingly, the value is derived when you start having things like voltage or other things in various forms. And even then, getting the right voltage and the right kind of data is important to deliver on some of these outcomes. It's very common that we will talk to, I've got voltage data, but there might be average voltage over a 1 hour period, is not that useful for doing something like a phase identification program as it is if it was instantaneous voltage, at that period. So there's all these kind of nuances about the right data, but that's part of that whole visualization process, and becomes very obvious when you start looking at it in areas where you want to improve, and off you go. But often, regardless of what you have today, you can already start to add value and see value by just looking at your network and where some of the challenges are. And I think that's one of the things we did learn from the EPRI program, with the Fortis and the VEC teams, that even though it maybe wasn't expected or what we were focused on, just once you started looking at some of the graphs over a longer period of time, you could start to see changes in the network that maybe weren't previously maybe visible or we were aware of, and so that's really, really important, and starts to raise then more questions and interest to drill down into what happened here. Well, network switching here, okay, that's not really a fault or an issue, but okay, that's interesting, we can see that happening. Or we did switch the network here and it didn't seem to do what we wanted, what's going on there? And that will lead to a whole range of different conversations, but it's the starting point of the conversation. So yeah, integration is kind of, understand, but visualization is your first step. So get it up and running, make sure you can see everything, context of your network, the best you can with what you've got, and then start to get into your analytics. And because from there, you can start to do a whole range of different things. As you move forward, we talk about network model refinement. So we want to better improve our meter to transformer mappings. That's a common one. Your phase identification. As you get into DER, things like the size of the inverter sizing will be an issue. I'll talk about that later a bit, but that's really interesting. You have a whole range of compliance things in your model to try and make it better, so your planning and activities will be more accurate. And then eventually you get to like what the utopian view, which is dynamic management. So how do I look at this data? How do I then make control decisions, whether it's to SCADA or to a future DERM solution, or even just to the field, and manage things in a more dynamic way and the reason you want to do that, of course, is back to the original start is, well, I've got a lot of solar, I've got these massive voltage fluctuations during the day. How do I manage that for my customers? Because, I need to manage that reliability and the impact it has on my customers. So we found this kind of approach, which each one of these could take you a long period of time. Sometimes you can skip a few, or if the vendor like ourselves might be able to help you accelerate them. That's kind of what we aim to do. But essentially, you need to follow a version of this approach to kind of add value. And what I'll focus on now is not so much the data integration and visualization. I'll show you the outcomes of that, but really, what are some of the analytical decision support things you can get started with that we've found to be super useful, relatively easy, but adds a lot of business value, we've found at least, to our customers. And I think these examples may not be necessarily 100% relevant, but I think the concept will definitely be. All right, so I'll start with this one, which is faults So we start with faults. When we get all that up and running, we give you the dashboard. Often what we do is we try some programs we might start like we did with the EPRI one, EV management, EV detection. We wanted to try and see how that would work and other advanced functions. But really, when we go to a new customer these days, maybe it's part of the lessons learned, is we'll just start with faults. Now, there's different kind of faults. It could be a brownout, it could be a fuse fault, it could be a safety fault, which is the one I'm going to show you. And the reason I've got a tap here is because in a network environment such as Australia's, we have the configuration is such that we have a neutral at the customer premise that tends to be connected and earthed to metal pipes in the ground, often near water pipes that are in the old days at least used to be metal. The most common fault, and what actually has been the first thing that every customer does with our solution, is start to detect safety faults where that earth has deteriorated. They call them neutral earth faults, or loss of neutral, or broken neutrals, where the current can then run sort of back through and liven up the metal pipes, where you get an electric shock on your taps or your gutters in your home, anything that's metal that it's earthed. Not as big a problem in North America, I must add, but it does happen. But it's definitely a problem over here. So this is a very practical thing. So that voltage data that we get can detect these things just like you'd use for any of the more advanced applications. But starting with something practical like a fault is something that can add real value to the business immediately. And from a sales perspective, it's really handy, because once we detect some of these safety faults, it's not uncommon that I'll receive an email from various managers who I've never met before, thanking us for that, particularly because some of them can be quite severe. And the example of that, just give us a sort of a sharing environment, is really what we call the neutral earth fault, which and here's a picture actually of one I found that we had solved, and this is really interesting what you can do. And this is out of the box stuff. This doesn't take much effort. Obviously, you've got to have the right kind of data and things, but just to give you an example, is it's hard to read probably on your screen there, but I'll maybe just walk you through it. So the top graph is impedance. So we calculate impedance when you got the voltage and the power triangle. If you're using Itron's old SSN solution, is very common for us to get that. I mean, ACU's got their own version. Interestingly, there's a lot of talk about calculating impedance in the meter and edge and all this. There's a whole with solar and with exports onto the grid, which will become a thing with EVs. You're going to find there's a number of challenges with that in real terms, but that's a whole nother conversation. But essentially what we're doing is calculating impedance, because your impedance readings will actually be erroneous in the meter, because they're kind of the export will make it look like something's happening, but actually it's not. So the example here is the impedance is tracking along. You can't really see it. It's like 1 ohm, or just under 1 ohm is what that kind of black line's showing. And something's jumped up. Now that's like 4 or 5 ohms. Now, for those that know, not so engineering centric, that's a lot. Like as in, if you touch that, if that was a fault on the home, you could die. Over here, and it has happened. So it's pretty serious. So this could be really bad, or your house could be burning down. This kind of jump is quite a serious fault. You can kind of see the voltage, there's voltage below. You can see these little wiggles. It's kind of always a bit of a sign that something's going on. You can also see these patterns back here, which is like something. If you look at the granular data, it will be even more obvious. It's starting to onset of an issue. The issue's happened, right? Now, what's happened in our solution, what we've done with most customers, is once we've seen something as severe as this happen, we automatically send a job to the field, gone through our testing so they're comfortable to do that. And the field crews got that, prioritized it, gone out, and you can, it's taken them a few hours actually, which I'm surprised about. It's taken them a few hours to go fix it. But you can see right here, this little part in the graph, that's when the meter's gone offline. They've taken them off supply for a bit, they've fixed the fault, taken a bit of time and started to the reasons for it is a bit of lag on the data or what does that, but essentially it's come back and you can see it's gone back to normal status and voltage is stable and everyone's happy. And you can see this is current down here. Current's increased at night, but voltage is stable. So everything's pretty good. So from a from a sort of a power quality perspective, you're going, fault happened, fixed it, restored to normal, it's all safe. And this is a scenario that, happens all the time. That's probably my extreme example, but probably an interesting one about how practically you can use this data just to make real impacts to your customers immediately. And I was just one customer to one of the field crews about how they use the product and getting feedback for improvements. And the one thing they said to me, which really struck home, is now, because when they go to site to tell them there's a fault like this, they're being proactive. And customers really appreciate that. Apart from all your safety, reliability benefits, of course, there's some benefits there, but the big benefit we've found is actually in the customer experience, because the field crews and you as a utility are being proactive. So very relatively simple thing, but very powerful in terms of impact. And just for those who really care, this is actually what the fault was. I got the guys to send me a photo. I'm not the expert on this. I think MCB means main circuit board, I think. But essentially, you don't have to be, I don't think, like an electrician to really suss it out. But it doesn't look good. It's corroded. It's created this fault. They went and fixed it. Customer's safe. And it all happened proactively. Right? You can do that off your voltage data or your power quality data from AMI pretty quickly and pretty easily. So that's one thing that. Go ahead.
We just have a question online. It says, why didn't the voltage reduce at time of meter reinstallation?
Yeah. Here's where it happened. I think that would be the outage. I'm just guessing here. I was took as a photo. This is the outage. So our voltage dropped to 0. That's why you got a gap down here. Just the way the graphs work. So that's when so I think the impedance you're probably talking about, that the voltage is fine. The impedance, I think that's just to do with, I have to take it on notice. I don't know, but there must have been a bit of a lag in the way that the impedance has been calculated before it went back down to there. So I take that on notice. I would expect it to drop too, but I don't actually know is the answer. But yeah, the idea, I guess, is that it will drop down to a normal state and get back going. There are some calculations around the way it works. It's not just the way we calculate impedance anyway is a much more complicated story. It's not just calculate the basic Ohm's law approach, although it is. There's a number of other factors we need to take into consideration to get an accurate lock on what's going on, particularly when you've got solar and other export factors on there, because it actually creates errors or it misleads you when you look at the numbers coming out of the meter on what the impedance will actually be. I.e., it's not actually what it is. You'll get really high numbers when actually it's not really high. So I think what's going on here is it's during the day. There's probably some export going on, and the numbers weren't necessarily reflective of what was happening. And then in the evening, as you can see here, when its exports dropped off, it's kind of corrected back down to here. That's what I suspect's going on, but it's probably beyond my pay grade in terms of explaining it in precise details. Sorry about that, but that's kind of the rough idea of what would have happened. It's very complicated actually getting impedance calculations right using this data, particularly in a DER environment. It's not as simple as it seems, we found, and we've done a lot of work with our customers to make sure that when we do calculate things and trigger these faults, that there's no false positive. Or when I say no false positives, I think anyone that says there's no false positives is lying. There's always false positives, but you want to minimize them for the field crew as much as you can. But the interesting thing in these scenarios, even if it wasn't this particular kind of fault, this would have been a fault of some description. So you're not wasting a truck roll in this case. So sorry about not being super explicit. I guess I'm the sales guy more than the engineer, but there probably is an explanation. And if you want, we can explain it to you offline. Hopefully that's okay. Is that okay? I didn't want to, unless we wanted more explanation. I'll go with yes. Right, so that's
good. Thank
sorry?
You.
Yes,
that answered the question. Thank you.
Yeah, hopefully well enough. All right, so that's just one example. Just another example which you'd be more familiar with is once you start doing that, you can do all kinds of really interesting things. So, really simple stuff like brownouts. I mean, this looks like a brownout, but if you look at the duration here, when I looked at it, it looks like a brownout. It was flagged originally as a brownout, but actually the duration is quite long. It's a couple of days, if you can read that. Right? It's very recent. So just so you know, in our dash, kind of way of looking at it, here's a long-term trend. So I can see there's been a change in voltage. I look at the details. Here's what's happened. And in fact, I looked at the notes from this is possible brownout because it kind of looks like a brownout, but actually I think it was an HV fuse fault of that transformer or something similar to that. That's why it was out for a couple of days. In this case, this customer hadn't raised the ticket to the field. I think they did eventually, and there you can see it's been restored. So these kinds of voltage fluctuations, like just looking at the variance of voltage against the norm, is a very useful way, and a very simple way actually, of finding problems in your network. Because when this kind of stuff happens, irrespective of what it is, it's something wrong. And so when you go out there, there's something going on in your network that you want to get onto. So we have a particular analytics thing called general network faults that literally just look for their voltage profile is looking for certain deviations in voltage with a bit of intelligence around it. But essentially what we've found with customers is that's a really simple way of detecting network anomalies that they can farm out to the various people in those regions to either look at, resolve. And they're often things like, might be just a brownout, which is more maybe something like an EV related thing that's maybe transient, but in this case it was more of some sort of fuse fault as an example. Or something more severe like that safety one we were talking about before. So even just looking at the voltage profile, which is very, very basic, you can do a lot with that, we found, and get a lot of value into the business with really not doing anything too complicated in the context of analytics. And by the way, just for for sake, so this is, I'm looking at the transformer level here. It's probably not obvious, but this is a transformer. That's its profile. Something's wrong there. What I did when I was looking at this before, I went up to the feeder, because in our system, we've got that. We mentioned we had the network topology, so I've got the relationship between, say, meters to transformers to feeders to the substation and anything in between. We've got phase and things like that. So what you can see here is the profiles, just for information, of all the transformers on that feeder. And you can see I just highlighted the one that we were looking at for that period. You can see, so without much effort, just visually and quickly by clicking on a few buttons, you can see that, well, is that a network related issue or is that localized to that transformer? You can see straight away that if it was a phase based issue or one phase was down or there was a network issue, you'd see other behaviors with these profiles, of course, with all the other transformers, okay, this one had a problem. So that's just another quick example of how the visualizations, even without analytics, just by looking at them, can help you identify these kind of anomalies pretty quickly, actually, and really simply. And your guys and girls will be able to do that because they're experienced and they know what this means usually by just looking at it, and get a lot of value, we found. And that's just a quick example. So yeah, I looked at detected it at the transformer level. I click the button, go have a look. Well, what's the feeder doing? Oh yeah, it's just this one transformer. Okay, so it's got to be localized to that. So let's go check that out. Obviously, so that's just a quick example of making some key decisions to speed up some reliability restoration. So there's some examples. Now the other one, once you get into DR, so once you got putting a bunch of inverters in homes, which will happen, whether we like it or not, customers are installing your electric vehicles. They may or may not be telling you. I know we all want to know, but it may not. Solar, a bit different. There's a lot of regulation around that here, but they do that. So with the regulation, for example, you apply for a connection or a connection agreement with the utility, and you get you get approved a certain size. For example, 5 kilowatts or 7 kilowatts, whatever the sizing is these days, and that's what you put in. These days, they also, which is not, we're working with some of the folks at VEC recently on this. I think with some new customers actually similar, you don't necessarily have export limits yet set in the rules for some states. So we've just been explaining actually, better get onto this, because once you get a lot of this stuff, the export may become your predominant issue on your network over demand actually, which will be really interesting, because that's what we're seeing in Australia. So we set export limits for all homes, various rules around that, and the idea is you need to maintain that, and it's all about capacity management, simple terms. But what we're finding after working with most of the utilities here and doing compliance checks is the export limits are not being adhered to because they've haven't been setting them up correctly. We've got mechanisms over here that mean that if the voltage rises too great, there's some automatic, it's kind of your volt via response, which you'll hear about to try to offset some of that voltage rise, and even just the size of the installation that you've been approved for. I think something like 60-70% of the time of everyone we've looked at, and in Australia that's probably nearly all of them, is non-compliant in either one or all of those measures. So they've got double the size inverter than they were approved for. They're not adhering to their export limits, etc. And this is just an example of an export limit breach, which we're detecting, saying, well, it's hard to probably read, but it'll be a limit. It's over the limit. We're seeing it, what's going on. It shouldn't be happening. And so utilities are now starting to, and our customers are particularly trying to really get onto this. And the reason they're getting onto it is because you're all working on, in various forms, on hosting capacity models, your state estimation at the feeder level, and a lot of the assumptions that are getting driven into that, particularly around DER, are these things. How big is it? How much of it is? If you're dealing with exports, you've got some assumptions you've made in your plan around that. Now, if nobody is adhering to any of those assumptions, which is kind of what we've been finding, then a lot of those plans are kind of out the window before you even begin. And it kind of matters because your investment, some of your investments and upgrades are going to be based on that. So we've been really focused on something, and again, it's simple. This is not AI and very complicated analytics. There's some really practical things you can do with the data you've got. This is just kilowatt hour data too. So this is probably even more relevant, that you can start to really manage this as it gets going, as it sort of starts to build in your networks. So you can get on top of it early and get your policies and procedures in place, so you try and mitigate that when it gets to scale. Because obviously it doesn't matter if it's one or two, but when you've got 50%, which will happen, I think, with EVs particularly, it really matters. So just another one to think about, which is pretty simple, but adds a lot of value to your business using the data you've got. And it's not super complicated. Okay, so that's kind of some examples. I'll talk about some faults and some compliance things that are, and I think the main message here is there's a lot of things you can do with that data. Once you've got the visualization sorted, it doesn't need to be super fancy analytics to add value. And we've found that to be a really good way of getting traction with programs and utilities, get the business engaged, get different stakeholders engaged, and get them using the outcomes of the project you put together, because that builds a momentum. And from that momentum, more advanced things, that summit, can be achieved. And so I was just going to show you some examples of what some of those future things we talked about the early stage, some of these more advanced things that are being done, just for and then what we're doing with other customers. And the most popular one that we get asked about is mapping of meters to transformers. Most common problem, common request. I think phase ID might be the other one, but generally I reckon this might be the most popular request. And so here's an example of this actually in action. But the idea, effectively, once you've got voltage, particularly, you can use a whole range of techniques. And you can Google this and find, papers from PhD people for the last 10, 15 years on how to do this in different ways. So it's not like a revolutionary bit of IP from Future Grid, but it's something that is very popular and that we help customers with, and I'm sure there's others that do it as well. But the idea is effectively, you can see, and I'd use this one because this one to me is obvious. You can see this is looking at effectively a transformer profile, remembering we've got sometimes much bigger three-phase transformers here. So we might have 200 customers on a transformer. So we've got so many profiles. But the grouping, you can see the clustering of the green, the profiling is kind of following a pattern. This one deviates a little bit. And this red line I've just highlighted, it's kind of red and the blue, you might see it there a bit. They're kind of, it's obviously not it's obviously at a different voltage level to that green one. And so what we're really saying, it's not clear here 100%, but what it's saying is that red one is probably, that red line is probably connected to the red transformer, not the blue one that we think it's currently connected to, just by looking at those voltage profiles. And from doing that, and there's varying degrees of accuracy you can achieve, depending on the granularity of the data, how long you look at it, but we've found you can clean up quite a lot of your relationship issues with this pretty easily by just looking at these profiles. And obviously that's automated. Interestingly though, when we do this with customers, the issue is not the detection. You can get that pretty easily. There's a lot of outliers day one, that some quick wins across an entire network of say 1 million endpoints. But the hard part then is, what do you do with that? So now I've got all these now I've got all these discrepancies. Now I've got to put that back into my GIS. Now, I think this is where what we try to advise customers is like, well, yeah, so we can detect it, but now you've got to update your GIS. And if we find 100,000 anomalies, that in itself becomes a new project, unrelated to us necessarily, but it's not insignificant, because it can be quite hard. We know one customer in particular who we were doing this for. The bigger cost for their business case was not this part of it, the detection, it was actually the fixing it part in their existing system. So sometimes we forget that the flow and consequence of these things is I have to fix something, and that can be not as easy as it may seem. Different people have different experiences, I'm sure. So that's a good one. The other one, which I'm getting more advanced stuff, is as you get into the DR world, as you want to manage it more dynamically, managing your exports more dynamically, so not just having a fixed limit, is becoming more popular. And the reason is because they want to increase the amount of benefit customers can get from their DER, from their solar, from their EVs back onto the network without impacting the capacity. So really they're trying to manage it more dynamically, and that's where your DERMS comes in, or your virtual power plants, but mainly DERMS. So we're doing this with a couple of customers. It's still pretty new. So everyone's still trying to figure it out. But the idea is that if you manage it more dynamic, if you've got the visibility, you can figure out at the point in time where your network is constrained using that hosting capacity stuff I kind of mentioned earlier. And then you can start to turn things on and off at certain times of the day to maintain capacity. And the idea, of course, is to avoid further investment. So that's an advanced kind of control thing. So that's something you can do using that same data. And customers are. And finally, one of the most popular ones when it comes to control is what we call voltage management. We spoke about the voltage spread, high to low, because of solar. This is something that it can be a coarse way of managing it is by just adjusting your taps in your zone subs, with the SCADA. Obviously, you need the equipment to be able to automatically do those, whether it's a set point setting adjustment or tap setting adjustment in your zone sub, but you can do that, and increasingly we're doing that with customers here. And really the idea, in simple terms, is to just maintain this. If you think about these two lines as your voltage upper and lower bounds, and this is the spread of voltages at a particular day time for those zone subs overall, this orange line, you're trying to maintain as much of the things above the line back into the, to your normal range. So knowing the tap setting you're currently at, knowing the spread, you can make a pretty informed decision, and you can do this kind of in near real time, and we do, to inform and change those set points to try and move things back into compliance. And then as the sun goes down, you kind of do the reverse, right? Because the opposite may occur. So that's a technique that's being adopted for people today that's a bit more advanced. Obviously integrated to SCADA. You're in the OT zone. There's a lot of other things to discuss, but that's kind of the space that we end up sitting as a solution to manage these kinds of control-based decisions using this data. But as I said, that's not where you start. That's kind of maybe where you end. And that's kind of it for me. Hopefully, it looks like I might have actually got right on time too. Maybe I went too long. I'm not sure. Sorry if I did, but I do like talking.
No, this is perfect. Thank you. I don't think we have any more questions online. I will get the presentation and the recording posted to the Incubate Labs website shortly. And thank you all for attending. Chris, did you have anything else? Ed, did you have anything you wanted to add?
I guess the only thing that I would add is that having worked with these folks at Future Grid, they're as they would say in Australia, a good bunch of blokes. And so it was a pleasure.
Thank you, Ed. And we did pay him for that, so the checks. All right. Well, if no one's got any questions, have the deck. If anyone wants any follow-ups or just reach out to the team or us direct, happy to help. Happy to explain anything in more detail, or even if you just want some advice about the data you need for your own programs, irrespective of our software, feel free to reach out, and we're happy to help. We love this stuff, and we're all about helping you adopt these new things into your network. So feel free to reach out.